Okay, so scientific uncertainty is an aspect of experimental science that is pretty critical. It has to do with making sure that your results are actually correct and that they're good. So there are two aspects of uncertainty. The first is accuracy, which is that the method of measurement is correct, is a measure of how correct the measurement is. And there's precision, which is the consistency of repeated measurements. Uh, Experiments with very high precision are usually extremely impressive, especially to untrained observers, because they'll give you a fantastic number of decimal places in their numbers. They'll measure very small, tiny quantities that are easy to measure, but they're only really actually impressive if the thing that they're measuring is measured correctly, because you don't want a very precise measurement of something that's wrong, because that means that the whole thing is not correct. So your kind of first priority is to have an accurate measurement, and your second is for it to be very precise. An example of how you could do something inaccurately is has to do with well, I'm going to provide an example from CERN. CERN is kind of the leading experimental consortium of scientists and physicists. These are the guys behind the Large Hadron Collider, for instance, and who discovered the Higgs boson particle. So back in, I think it was 2011, CERN had a neutrino experiment where the scientists running the experiment reported that they had measured neutrinos traveling faster than the speed of light. Now, the general attitude in the physics community at the time was that this was not a valid measurement, that it wasn't accurate, because um, every other experiment of this kind had definitively shown that nothing travels faster than the speed of light, including neutrinos. So most people were just waiting for them to figure out what they did wrong to give an inaccurate result. And a year later, they reported that they had discovered a faulty wire, which was responsible for the inaccurate measurement. So in this case, you have something like the same guys who made the Large Hadron Collider, like a very important and significant experiment. Um, they got an inaccurate result because some of their wiring was broken. And that's because their instrumentation is so complicated that you can't really easily know if it's working the way you intended it to, because to verify that you would have to check everything from the top and bottom, and all the logic would have to be correct as well. And sometimes things slip through the crack just because it's too complicated. So this is one reason that it's important that different experimental groups using different equipment arrive at the same results, which is an unfortunate thing when it comes to particle physics, because there's pretty much just one game in town right now, which is CERN. In the United States, we have Fermilab, but their support and funding isn't quite as much, and they're kind of winding down on quite a lot of experiments because they're considered redundant. Um, and I'm not really advocating for increased funding in Fermilab. I'm just really saying that you should be suspicious of measurements that are only coming from one experimental group, because even if they're very honest and they're working very hard to get the right results, if there is not another group with another set of equipment that works differently and that was set up by different people, you can't be reasonably sure that there isn't something wrong with the instrumentation of one of the two groups. And by having multiple groups arrive at a result, you can at least hope that their errors are different, and whatever mistakes one group make are different from the mistakes the other group made. Um, okay, so we can visualize the concepts of accuracy and precision using these bullseye targets. And the main difference is that in real life, when you're doing scientific work, you can't actually see the bullseye, you can just see the dots. Um, so the bullseye is something that we're providing because we know there is something called the truth when it comes to scientific measurement, and it's where we want to be, is at the center of the bullseye. And an accurate measurement will yield results from repeated trials that center around that truth. Whereas an inaccurate measurement will yield from repeated trials data that is off center from that truth. So on the right hand side we have inaccurate data, and on the left hand side we have accurate data. However, you can see that the data on the right is very clustered together, which makes it precise, right? The repeated measurements will give you very consistent results, but they aren't accurate. Okay, and so that is the video on accuracy and precision. Okay, so now we're going to talk about uncertainty as it is reported numerically. And so the first example is going to be what's called an explicit uncertainty. And I apologize if you can hear my newborn son in the background. He's being fed by his mom, and you're probably going to hear him grunting and crying a little bit. He's only about 6 weeks old. So apologies ahead of time. There's not much we can do about it. We'll just have to try and muddle along. So this is called explicit uncertainty, and the idea is we're trying to measure this object here, and we have it being measured with a ruler, but obviously any ruler is going to eventually have to stop providing markings. For instance, a typical ruler is going to only provide millimeter markings as the smallest division that's clearly labeled. And so every measurement process is going to have some point where the thing you're measuring is between two of the given markings. And in that case, you have to guess about how exactly far in between the object is. So if you look at it, it looks like this guy's about dead in the center. Now, I can't say that for sure because I don't have markings to back me up, but he looks like he's in the center. So I am going to estimate that the actual length of this object is 1.25 centimeters. But I could be off a little bit. It could be a little bit more, it could be a little bit less. Now, a really conservative estimate would be that I'm off by half a centimeter, but that's a little bit too big because that would be this entire division here, right? And if I'm off by half a centimeter, that would be putting me in the other markings, right? And so that's a little too big of an estimate of my uncertainty, and it's not really very accurate. So a more accurate estimate would be to say I could be off by about half of this division here, which is 0.25 centimeters. So because it is reasonable to say that I could be about 2.5, half of that division in either direction. And I know that it'd be a little too extreme to say that I'm all the way in the next marking, so it might even be smaller than that. But it would be reasonable to say maybe I'm within 0.25 centimeters of the correct answer. Now, just what exactly you put here is the judgment of the experimental scientist. Sometimes you can determine from the rules of probability exactly what number should go there, and other times you have to use your best judgment. What I would usually say is that we can easily distinguish markings visually up to a quarter of a measurement, right? If I had 1, 2, 3, 4 subdivisions, I can be pretty sure about something within a quarter of that. So if I were going to do this, I would say give or take 1.5 over, or not 1.5, but 0.5 over 4 centimeters, which would be 0.125 centimeters. The rule, generally speaking, when it comes to writing down explicit uncertainties, is don't overstate your uncertainty and don't understate it. So overstating it would be saying it's completely uncertain and we have no idea. And understating it would just be saying I know exactly what it is and I have no doubt about the actual true value. And the truth is usually somewhere in between. and it takes a little bit of skill and finesse to decide what that should be. Now, on the next page, we're going to do an example with significant figures. And one thing about significant figures, or significant digits, as they're sometimes called, I'm going to alternate between calling these significant figures and significant digits, is that you really need decimal divisions on your measurements. So it's really, really difficult to do significant figures when you're using a ruler that has like inches, because usually a ruler with inches has like 16ths of an inch or 1/8 of an inch markings. And you really need decimal divisions, like a tenth of a unit divisions, for significant figures to work. But significant figures are sort of a shorthand to keep from having to write the explicit uncertainty over and over again. And so the whole idea here is now we actually have proper markings, and we can see that the value is between 1.2 centimeters and 1.3 centimeters. But it's somewhere in between. And so I still have to guess how far in between. And from this picture, visually, I can really only kind of say it looks like it's about halfway, but I'm not sure at all how much. So I'm going to say it's 1.25 centimeters. Now the thing is, if I go with my rule of using half of a unit of division, then I would say this is 1.25 centimeters, give or take 0.05 centimeters, because this distance here is a tenth of a centimeter, and so half of that would be 5/100ths of a centimeter. So this is the explicit uncertainty, but with significant figures, I would just write 1.25, where it's understood that this last digit on the right here, this rightmost digit, is a guess. So this is my first guess when I'm reading off the ruler. So what does that mean? Well, the 1, that's not a guess, right? Because it's bigger than the 1 centimeter mark. The 2, that's not a guess because it's bigger than the 1.2 centimeter mark. It's the 5 that's a guess because I'm guessing how far in between 1.2 and 1.3 the measurement actually is. So this guess is what's called my least significant digit. And the 1 is what's called my most significant digit. And the idea is the 1 is the digit I am the most sure of, and I'm even really 100% sure of the 2. But the 5, I'm not really sure if that's actually the right number. It could be 1.24, could be 1.26, or something else, okay? And the whole idea is that there's a whole range of decimals around here that it could be some very specific value. For instance, the true value could be 1.256788889, but all of that is being lost in the noise because my measuring device only allows me to guess up to this digit here, which is my least significant digit. And so when I'm combining numbers that are represented in terms of significant digits, I need to keep in mind that that uncertainty is going to affect the results. And so there are rules for when you combine significant figures together using arithmetic operations, which is going to be in a separate video.